So now we're going to go over the different components of the scientific method. You probably encountered this before at some point, but it's so crucial to the way that we conduct scientific research and the way that we build knowledge that it's worth going through again. So in this video, we'll outline the main components of the scientific method and compare them to some other types of human knowledge structures. Okay, so what does science mean anyway? The English word science has a Latin root, scire, which means to know. And that's all simple enough, but interestingly, that's derived from another word in Latin, scindere, which means to cut, to cleave, or to split. This in turn comes from a much older Sanskrit word, chinadi, which also means splits or cuts. So this etymology is nice because it captures what's really at the root of the scientific approach, which is to take a massive question that on its own is intimidating, maybe unknowable at first, but then cut it down into much smaller and more approachable frameworks and questions that can start to be answered, addressed, and then built upon. So for instance, you could start with a big nebulous question like, what happened to the dinosaurs? You cut it down into more concrete statements, such as, if an asteroid killed the dinosaurs, then there should be a crater that's exactly as old as when the dinosaurs disappeared. That crater would also have to be of a certain size in order to kick up enough dust to block out the sun across the world. And that dust would have to have fallen everywhere on Earth, including at the bottom of the ocean. So we can look for it there. It should be the same age of the crater that we think is responsible. So in this way, we can start to build different observations into a theory that can start to address these questions that seem really intimidating at first. So let's consider some actual definitions. If you go to Google, which draws from the Oxford Dictionary, science is defined as the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. Then, if you want another definition, you go to Wikipedia to find something similar. Science is a systematic enterprise that builds and organizes knowledge into the forms of testable explanations and predictions about our universe. And finally, if you go to another encyclopedia, let's say Britannica, and you see this definition, science is any system of knowledge that is concerned with the physical world and its phenomena, and that entails unbiased observations and systematic experimentation. In general, a science involves a pursuit of knowledge covering general truths or the operations of fundamental law. So you can see there's a few words that are highlighted because they're in common across these definitions. You'll see knowledge, which makes sense, that's not too surprising. You'll see things like experiments, examining. And these are getting into the idea that you're observing things impartially. You'll also see the physical world too, and this is important because there are a lot of immaterial subjects that science isn't really equipped to study. But to me, the most important word here is system. Science isn't about being smart or blowing stuff up in a lab. It's about doing these things in an organized or systematic way for a purpose so that others will accept your results and build upon them. And it's through this systematic approach that we can start to build really elaborate answers to questions that once seemed too intimidating to answer themselves. We can represent the system as a cycle. So let's go through the main components of the scientific method. This process usually starts with some kind of observation. This can be based on your own senses in the world or from the things you read. This should lead to some kind of question. And then this question then leads to a hypothesis, a guess at the controlling factors behind the observations, and a possible resolution to the question. So in order to see if your hypothesis is correct, then you'll need to conduct an experiment or comparison. This is often going to have a structure like, if X is correct, then Y should happen. And then you do the experiment to see if Y happens when X happens. The most important part is that this is an iterative process. So if Y doesn't happen, then you re-examine your prediction and your experimental design. Did I do the experiment right? Could the results be caused by another factor? How do I really know that? And just on a personal note, it's actually very rare for hypotheses to be absolutely correct the first time through. And this is often a sign that your initial question doesn't go far enough. Anyway, even though it's a small part of the cycle here, my experience suggests that you'll spend 90% of your time stuck in this whirlpool, either because you're trying to figure out the best way to do the experiment, or because the measurements you made have some uncertainty or scatter to them, and you need to think carefully if your results are reproducible or not. But so once you've gone through the cycle enough times, you'll be able to take the results of your experiments and draw conclusions from them. The combination of multiple hypotheses can be synthesized into a theory, which will explain many observations. If you manage to do this, your theory will inevitably have some implications. These are the observations that will lead to new questions, new hypotheses, new experiments, and on and on. And so even if it's presented in capital letters and has a really formal thing, it's important to realize that the scientific method really just encompasses steps that you do all the time in your daily life. For example, if you're in a room and the lights go out, that's an observation. You'll naturally have a question, why did the lights go out? And this might lead to a hypothesis. Someone turned off the lights. And then an experiment. If I turn the light switch, the lights should come back on. So the important thing here is that this is falsifiable. If I flip the switch and the lights don't turn on, then the hypothesis is invalid. This leads to some data, which are observations, in this case, made by your eyes. So let's say you flip the switch and the lights stay off. Now you rejected your initial hypothesis and need a new one. So you think, what if the light bulb broke? And then this leads to another testable prediction. If the light bulb failed, then if I turn on the TV should turn on. We can keep going with this scenario. If the TV turns on, you provide evidence in support of your hypothesis. Then you can make another experiment that if you replace the light bulb, it should work. Congrats, the light turns on. It seems like your second hypothesis is correct. And so by compiling different types of observations, you can start to compose a theory. Let's say you notice that the clock on your microwave is reset. Then you can form a hypothesis that this happens if the power goes out for 2 seconds, and that the microphone clock will reset anytime this happens. This leads to an experiment. If I unplug the microwave, plug it back in, the clock will reset. So now if this works, you have multiple confirmed hypotheses. You can start to develop a theory about a power surge, perhaps. You can continue to test this. You can ask your neighbor if their power went out. You can check out the power company's website to see if they've announced anything. These are examples of independent replication. So I'm sure you get it by now that this process is so common that it borders on mundane. At the same time, what's remarkable about this approach is that it still works when tackling big questions about our oceans, our world, and our universe. You'll see some of those throughout the semester. So it's probably good to define some of this vocabulary in more detail. I had to pay attention to this because it'll probably come up again on your quizzes and tests. So to define a hypothesis, it's a tentative statement about the natural world leading to deductions that can be tested. If deductions are able to be verified or corroborated, it becomes more probable that the hypothesis is correct. But at the same time, if deductions are incorrect, the original hypothesis is definitely falsified and needs to either be abandoned or modified so that further experiments can evaluate the modified hypothesis. And then when you have multiple hypotheses that have some evidence behind them, they can be aggregated together to form more complex inferences and explanations. And this is how theories are developed. Before we talk about what theories are, we should really define what a fact is, because this is often used differently in public conversation than it does sort of in the science world. Facts to scientists are confirmable observations. Hypotheses or theories may be supported by facts, but they themselves can never become facts. So what's a theory? In science, a theory is a well-substantiated explanation of some aspect of the natural world that can incorporate observations, inferences, tested hypotheses. The key thing here is that theories are able to be tested, and even if old and widely accepted, they can still be overturned by new observations. Furthermore, you can never really prove that a theory is true, just that it is exceedingly likely and that all other proposed theories are incorrect. Sometimes in casual conversations, though, you'll hear the word theory as a synonym for the word hunch, and this is totally wrong. You can go back to the light bulb example, and you can say, I have a theory that a ghost caused the power surge in my apartment. But this isn't a scientific theory. This is just a hypothesis, and it's a bad one because it's really hard to falsify. You can't really prove that ghosts don't exist, and you can't disprove they exist. So it's not very useful. But in a scientific sense, a theory is the end goal of scientific observations. It explains what you've observed. Okay, and last, let's talk about scientific laws. You might be familiar with the law of gravity or the laws of thermodynamics. Laws are statements of extremely predictable phenomena, and they're often expressed as an equation. And laws are pretty amazing because they're quite good at predicting future observations. The force of gravity tomorrow will be the same as it is today, will be the same on Earth as it is the moon. But at the same time, these laws don't offer explanations as to why gravity exists. So this is where theories come in. This is what theories do in science, is they explain observations and they connect different observations and laws and facts. Okay, so scientific theories can never be proven true. Evidence can only be brought in to support them. However, a single observation can disprove a theory, and theories can be replaced if the new theory is better at offering more consistent explanations of existing observations. This means that even old, well-established theories need to be testable. So there's a few theories that are generally disproven. You'll see some popular examples such as flat earth theory, geocentric theory, creationism, spontaneous generation. The phlogiston theory is based on this mysterious substance that's released in fires, and that's really been replaced by modern chemistry and the understanding of elements. On the other hand, there's some generally accepted theories, such as evolution, relativity, germ theory of disease. We'll talk about several of these throughout the course. So science has been a major mechanism for humans to generate knowledge and has been happening for millennia, even if it hasn't been formalized as the modern scientific method, which has only happened in the last few hundred years. But it's useful to compare science with other ways that humans have tried to explain observations and synthesize knowledge. Let's start with philosophy. So even though the PH in PhD stands for philosophy, so you can be a doctor of philosophy in oceanography or in biology or in physics or any other science. Modern philosophy is distinct from modern science. The word philosophy is really derived from the Greek meaning love of wisdom. And you can further look into the etymology of wisdom, which really relates to the sense of being skilled, being crafty, or clever. Philosophy focuses on how and why the world is what it is, and how and why we experience it the way we do. The main tools of philosophy are logic and reason, and these are often applied to solve intangible problems that science cannot address. These are questions like, what does it mean to exist? What is an ethical life? What does it mean to feel? What is good? In philosophy, these answers are mainly won by logical proofs. And this is a key difference because science can only really disprove statements. It can't prove that they're correct. And it can only disprove statements if they can be measured somehow. So there are a lot of things that philosophy can address that science still can't touch. So let's move on to science and religion. One of the really central activities in science is the doubting of hypotheses, trying to prove them wrong or modify them with new evidence. And this is in contrast to most religious systems, which are based on this idea of faith. Faith in English comes from a Latin word, which also means to trust. And you can see this root also appear in words like confide. This is based off of the complete trust in or confidence in a person or thing, such as a supernatural power, religious teaching, religious elders, etc. But because religious explanations rely on supernatural forces, they're not testable and they're not changeable. And so this is one of the things that differentiates them from the scientific method. At the same time, science can only present testable theories, so it can't really enter into this realm of the supernatural. Subjects for science have to be able to be measured, they have to be able to be falsified. And so much of the separation between scientific inquiry and religious inquiry is really separated by what's observable and what isn't. Science can only address what's observable and what can be replicated and what can be proven false. Okay, lastly, let's consider the distinction between science and pseudoscience, which is a term you've probably heard before. Pseudo also comes from Greek, meaning false, so this is a false science. Now there's a lot more information in the world, and a lot of it is super accessible through social media. And a lot of this information, is kind of disguised in the trappings of the scientific method. So what are ways to distinguish science from pseudoscience? The key difference for our context is that pseudoscience is motivated by seeking confirmations, but does not make verifiable predictions. Often claims of the flat earth or miracle cure for COVID can fit with a number of imaginable outcomes. So if hypotheses are presented, they're either not followed through on, or they're not specific enough that they're actually falsifiable. And just as a good example of this, there's a Netflix documentary that you may have seen called Behind the Curve that follows people in the Flat Earth Society. And I think it does a really good job of showing the pseudoscience fallacies firsthand. On multiple occasions, they show their members designing experiments, outlining specific hypotheses, even that if the Earth is flat, the curve of the Earth will change the position of something like a laser shining over a distance, stuff like that. But then when they do the experiment and they find evidence against their hypothesis, essentially they falsified it. But instead of accepting that the Earth may be round, they just throw out the data and try to design a new experiment that'll prove their ideas right. So this is really the key difference between pseudoscience and science, is what happens next after you've proved an idea wrong. Okay, so in this video, we've outlined the main components of the scientific method. The key thing here is that the hypotheses must be testable, observations must be reproducible, and theories must be falsifiable. Science is different than philosophy and religion because it only operates on phenomena that can be directly observed. Progress can only be achieved by ruling out and doubting existing hypotheses. So also remember to take the quiz that corresponds to this video and fill out the survey for your discussion section times, and we'll see you next week.